every second, Earth turns beneath silent skies, races around the sun, and travels with the sun through the Milky Way. Nothing feels fast, because everything nearby moves together, yet the still ground is part of a vast layered motion through space. In this documentary, the journey begins at the edge of the observable universe and moves inward, step by step, until the speed of a quiet human body becomes clear. Like and subscribe for more slow space documentaries, and drift into the hidden motion of the cosmos. Across the widest known scale, motion begins with space itself. The observable universe contains galaxies in every direction, spread through a vast pattern of clusters, filaments, sheets, and open regions called voids. At this scale, speed is not only the motion of objects through space, it is also the stretching of space between objects. Observations indicate that, on very large scales, galaxies are carried apart as the universe expands. The farther a distant galaxy lies from the Milky Way, the more its light is usually shifted toward longer, redder wavelengths. This redshift shows that the space between galaxies has grown while the light has travelled across it. The expansion is not an explosion from one central point into empty surroundings. No edge or centre is seen within the observable universe. Instead, every broad region sees distant regions moving away on average, because the fabric of space grows between them. The word fabric is only an image. In science, the expansion is described by the changing scale of the universe, a measure of how distances grow with cosmic time. Galaxies remain bound inside local systems, but the greatest distances follow this wider growth. The speed linked with cosmic expansion depends on distance. Nearby galaxies may move toward or away from the Milky Way because of local gravity, but very distant galaxies show the smoother pattern of expansion. Their recession speed is not like a spacecraft crossing a fixed background. It is the increase of distance as space stretches. At great enough distance, this increase can exceed the speed of light without breaking the rule that objects cannot move through local space faster than light. The galaxies are not racing through their own nearby space at such a speed. The space between regions is increasing. The observable universe has a horizon because light has had a finite time to travel since the hot early state. The universe is about 13.8 billion years old, but the most distant regions now seen are much farther away than 13.8 billion light years, because space has expanded while their light crossed it. Observations of the cosmic microwave background, the faint afterglow from the early universe, show a universe that was once hot, dense, and nearly uniform. That light now reaches detectors as cold microwave radiation from every direction. It forms a wide reference frame for describing motion on the largest scale. Against this ancient background, the Milky Way is not perfectly at rest. The temperature of the cosmic microwave background appears slightly warmer in one direction and slightly cooler in the opposite direction. This pattern is called a dipole, meaning a two-sided difference. It indicates that the Milky Way and the local collection of galaxies move relative to the early universe radiation. The measured motion is hundreds of kilometers per second. This is fast by ordinary standards. Yet it is only one layer within the larger description of cosmic motion. The expansion itself is measured through many kinds of observations. Distant exploding stars, galaxy surveys, and the cosmic microwave background all show that the universe changes with time. The expansion rate today is known with good evidence, although different measurement methods give slightly different values. This difference is known as the Hubble tension. Observations indicate that the expansion rate measured from the early universe and the rate measured from nearer cosmic distances do not fully agree within expected uncertainty. It remains uncertain whether this tension comes from hidden measurement effects, from limits in current models, or from new physics not yet understood. On the larger scales, the universe also appears homogeneous and isotropic. Homogeneous means that matter is spread in a similar way when averaged over enormous volumes. Isotropic means that the view looks broadly similar in all directions. This does not describe small scales, where galaxies cluster and voids open like dark oceans between bright shores. It describes the widest pattern, where the unevenness becomes part of a larger smoothness. The expansion belongs to this averaged view. The idea of speed becomes gentle and strange at this scale. A familiar speed usually belongs to one body moving past another. A planet circles a star moves through a galaxy, a spacecraft changes position against nearby objects. Cosmic expansion is different. It does not give every galaxy a single simple speed through space. It gives distance itself a rate of growth. A galaxy twice as far away tends to recede twice as fast in the smooth expansion, because there is twice as much space between it and the observer to stretch. Gravity resists this widening where matter is close enough and dense enough. Galaxies, galaxy groups, and galaxy clusters can remain bound, because their mutual gravity overcomes the expansion within their local region. The expansion is not tearing apart the Milky Way, the solar system, Earth, or ordinary objects. These smaller systems are held together by gravity, electromagnetism, and the forces inside atoms. The larger scale is therefore not a force felt inside a room or across a mountain. It is a property of the universe seen across millions and billions of light years. The fastest recession speeds belong to regions near the edge of what can be observed, where the distance has grown during the long journey of light. Some galaxies whose ancient light is visible today are now receding so quickly because of expansion that light emitted by them now may never reach the Milky Way. This does not make the visible light unreal. It means that the universe changes during the crossing of that light, and the current distance to its source belongs to a later cosmic time. In this outermost view, motion is layered with time. Light from remote galaxies shows them as they were long ago. Their redshift records the expansion between then and now. The cosmic microwave background shows an even earlier state, when atoms first formed and light could travel freely through space. The present universe contains the same broad expansion continuing, measured through the positions, brightness, and colours of distant objects. The great movement is steady in description, though not simple in cause. Dark energy is the name given to the unknown driver of the observed accelerated expansion. Observations indicate that expansion has been speeding up over recent cosmic history. It remains uncertain what dark energy truly is. At the outer boundary of the topic, all familiar motion rests inside this widening background. Galaxies drift in a universe whose distances grow. Light stretches as it travels. The Milky Way participates in the expansion only through its relation to the farthest unbound galaxies, while remaining held together inside nearer structures. The widest reality of speed is therefore not a single rush through empty space. It is the quiet growth of distance across the universe, measured by ancient light, shaped by gravity, and still not completely understood. Within the widening universe, the smooth expansion gives way to the uneven pull of matter. Galaxies are not spread like dust in a perfect mist. They gather along long strands and broad walls, with large, emptier regions between them. This immense pattern is called the cosmic web. It forms because gravity slowly amplifies small differences in density. Regions with slightly more matter pull more strongly, drawing in gas, galaxies, and dark matter. Regions with less matter lose material more easily and become wide voids. On this scale, the motion of galaxies is no longer described only by expansion. It is also shaped by flowing paths through uneven gravity. A galaxy inside the cosmic web has two kinds of large-scale motion. One part comes from the general expansion of space. Another part comes from the pull of nearby and distant mass concentrations. This second part is called peculiar motion, meaning motion that differs from the simple expansion pattern. The word peculiar does not mean strange in an ordinary sense. It means particular to the local gravitational environment. A galaxy may recede because space expands, while also drifting sideways or inward because mass is not evenly arranged around it. These flows are slow only when judged against the size of the universe. In ordinary terms, they are extremely fast. Galaxies can move at hundreds of kilometers per second through their regional surroundings. Clusters of galaxies can also have shared motions as they respond to the gravity of larger structures. The motion is not random like scattered sparks. It follows the shape of matter. Galaxies tend to move out of voids and toward denser filaments, groups, and clusters. The pattern resembles water draining across a broad landscape, although the true process is gravity acting through space over billions of years. The Milky Way lies inside such a web of matter. Its motion relative to the cosmic microwave background reflects the combined pull of many structures. No single object fully explains it. Nearby galaxies, larger groups, galaxy clusters, and broad regions of matter all contribute. Some of the pull comes from visible galaxies and hot gas. Some comes from dark matter, the unseen matter inferred from gravity. Dark matter does not emit light in the way stars and gas clouds do, yet its presence is measured through the motions of galaxies, gravitational lensing, and the growth of structure. In these large flows, dark matter is not a detail at the edge of the picture. It is a major part of the mass that guides motion. The cosmic web is mapped through redshift surveys, which measure how the light from many galaxies is stretched. A redshift survey gives positions along the sky and estimates distance from the shift in light. From millions of galaxies, astronomers build a three-dimensional picture of matter across great volumes. The picture shows clusters where many galaxies gather, filaments where galaxies form long chains, and voids where galaxies are sparse. These surveys also show that galaxies are not perfectly still within this pattern. Their motions slightly distort the redshift map, because a galaxy's own movement adds to or subtracts from the redshift caused by expansion. Large galaxy clusters are among the strongest visible landmarks in this region of motion. They contain hundreds or thousands of galaxies, along with hot gas spread between them and a larger halo of dark matter. Their gravity affects nearby galaxies and groups. Matter falls toward clusters along filaments. Infall means inward motion under gravity. It does not always lead to an immediate merger. Over vast time, the pull changes paths, speeds, and distances. A galaxy may remain outside a cluster while still taking part in its larger flow. Voids also shape motion. A void is not entirely empty, but it contains much less matter than surrounding regions. Because dense regions pull matter away, voids become emptier in relative terms as the universe evolves. Galaxies near the edges of voids can appear to move away from the void interior and toward the surrounding web. This motion is not caused by a push from empty space. It is caused by stronger gravitational attraction outside the void than inside it. The result is a quiet outward clearing, with matter gathering more strongly along the surrounding walls and threads. The expansion of the universe continues across this whole web, but gravity bends the simple pattern. In one direction, a galaxy may appear to recede a little faster than expected from expansion alone. In another direction, a galaxy may recede more slowly, or even approach, because local gravity dominates its motion. This is especially important at nearer distances, where peculiar motions can be large compared with the expansion speed. At far greater distances, the expansion becomes the stronger part of the observed redshift, although local motion still adds small details. The motion of the Milky Way and nearby galaxies is often described relative to large-scale reference frames. The cosmic microwave background provides one such frame, because it comes from the early universe and surrounds observers in every direction. When astronomers subtract the motion of Earth, the Sun, and the Milky Way, the remaining dipole pattern reveals a broader drift. This drift shows that the local region is moving through the universe with respect to that ancient radiation. The measurement is precise, but the full accounting of every gravitational contributor remains difficult. Observations indicate that nearby and moderately distant structures account for much of the motion. It remains uncertain how completely all mass contributions have been measured, especially where dust in the Milky Way blocks part of the view. The cosmic web also changes with time. In the early universe, matter was more evenly spread, with only tiny density differences. Gravity slowly deepened those differences. Dark matter gathered first into broad halos. Ordinary matter, made of atoms, fell into those halos, cooled, and helped form stars and galaxies. Over billions of years, small systems merged into larger ones. Filaments grew more defined. Voids became larger in relative size. The present motions of galaxies carry the memory of that long history. Each flow reflects both the current pull of matter and the earlier paths by which structures formed. At this outer regional scale, speed is not a single arrow. It is a combined drift through a changing landscape of gravity. Expansion increases distances between unbound regions. Gravity gathers matter into the web. Galaxies follow both influences at once. The Milky Way shares in this movement as part of a broad stream of galaxies, not isolated, not fixed, and not moving through a featureless emptiness. Its path belongs to the larger arrangement of matter around it, where clusters, filaments, voids, visible stars, hot gas, and dark matter together define the calm but powerful flow of the local cosmos. Within the broad cosmic web, the Milky Way belongs to a still more local flow of galaxies. This region is commonly described through the idea of Laniakea, a proposed supercluster-scale basin of motion. A basin of motion is a region where galaxies tend to stream along paths that appear to converge toward a common gravitational area. The name Laniakea is used for a very large collection of galaxy groups and clusters, whose motions are linked by the pull of surrounding matter. It is not a single bound object like a star cluster or a galaxy. It is a vast region outlined by the way galaxies move. The Milky Way lies near one edge of this region. Its motion is influenced by the uneven distribution of matter across tens and hundreds of millions of light years. In this scale of description, galaxies are treated like slow markers carried by gravity through the expanding universe. Their paths are estimated from distances and redshifts. Once the simple expansion is accounted for, the remaining peculiar motions reveal the direction of a local gravitational flow. These motions show that the Milky Way and many neighbouring galaxies are not drifting independently. They participate in a shared movement shaped by large nearby structures. Laniakea includes several known galaxy concentrations, including the Virgo region and the area associated with the Great Attractor. The Great Attractor is not a single object. It is a gravitational region, partly hidden by dust and stars in the Milky Way's disk, where the motions of many galaxies show a tendency to converge. because the Milky Way's own bright band blocks part of the sky. The exact mass distribution there has been difficult to map. Observations through radio, infrared, and X-ray light have improved the picture, but some uncertainty remains. The pull is real in the measured motions, while the full distribution of matter responsible for it is still being refined. The motion through this region is not a fall toward one final center. The universe continues to expand, and the structures involved are immense and loosely connected. Some parts may remain gravitationally related for long times, while others may separate as expansion continues. Laniakea is therefore best understood as a map of present-day flows rather than a solid cosmic island with a sharp physical wall. Its boundary is drawn where galaxy motions appear to diverge toward neighbouring basins of attraction. On one side, galaxies flow inward toward the same broad region. On another side, their paths tend toward a different large-scale structure. This way of drawing a supercluster differs from older methods that simply connected clusters by position. A positional map shows where galaxies are. A flow map shows how they move. Both are useful, but they do not always define the same borders. The Laniakea description emphasizes motion. It asks how galaxies respond to gravity in their region after the overall expansion has been removed. The answer is a wide pattern of streams, like many faint paths on a dark landscape, all shaped by visible and unseen mass. The Milky Way's participation in this flow is measured indirectly. Astronomers observe many galaxies, estimate their distances, measure their redshifts, and compare the expected expansion speed with the observed speed. Differences reveal peculiar motion. Because each measurement has uncertainty, the resulting flow map is built statistically from many galaxies rather than from one perfect marker. The picture that emerges places the Milky Way within a large stream toward the dense region associated with Laniakea. Observations indicate this motion is part of the same broad pattern seen in the cosmic microwave background dipole. Although not every detail of the dipole is explained by the nearest structures alone. The scale of Laniakea is difficult to hold in ordinary thought. It spans hundreds of millions of light-years. Light itself takes hundreds of millions of years to cross such a distance, even though light is the fastest signal known in physics. The galaxies within this region are separated by vast spaces, and most of those galaxies never interact directly. Their connection is gravitational and statistical, seen through motion rather than touch. A single galaxy is small inside this scale. Much as a grain of sand is small beside a continent, yet its motion still carries information about the larger gravitational terrain. The Virgo cluster is one important mass concentration within this local supercluster environment. It contains many galaxies and lies much nearer than the larger hidden concentrations behind the Milky Way's dusty band. The Virgo region affects the motion of nearby galaxy groups, including the local group to which the Milky Way belongs. Its gravity contributes to local streaming motions, but it is not the only influence. Farther structures also matter. The combined effect is layered, with nearer pools and broader pools adding together. The Great Attractor region lies beyond Virgo in the direction where many galaxy motions appear to be drawn. It is associated with large concentrations of galaxies and dark matter. Behind and around it, other structures also contribute to the wider gravitational field. One of the challenges in understanding this region is that motion does not point only to the nearest dense place. A galaxy's path reflects the sum of many pulls, including mass spread across very large volumes. A stream may therefore seem to aim toward one named region, while also being influenced by matter beyond it. This local flow does not give the Milky Way a simple speed that can be separated from all others without choosing a reference frame. Relative to the cosmic microwave background, The local region moves at hundreds of kilometers per second. Relative to nearby galaxies, the motion has different values and directions. Relative to the smooth expansion, the peculiar flow shows the gravitational response of matter. Each reference frame is valid for its purpose. None alone gives the complete meaning of motion. At the scale of Laniakea, the calm reality is that the Milky Way is carried within a broad gravitational current. It is not fixed in a cosmic grid. It is not simply expanding away from everything around it. It is part of a wide regional drift, guided by clusters, filaments, hidden mass, and the long memory of structure formation. Observations indicate the general flow with confidence. It remains uncertain exactly how every mass concentration contributes, especially where the Milky Way's own dust limits the view. The result is a measured but unfinished map, where the galaxy's large-scale speed is known as part of a wider, quiet movement through the nearby universe. Inside the larger regional flow, the Milky Way belongs to a smaller gathering of galaxies called the local group. This group is the nearest gravitational community around the Milky Way. It contains two large spiral galaxies, the Milky Way and Andromeda, a smaller spiral galaxy called Triangulum, and many smaller dwarf galaxies. These galaxies are not merely passing through the same part of space by chance. Their motions show that they are bound by gravity as a group. The expansion of the universe does not pull them apart in the simple way seen between more distant unbound systems, because their mutual gravity dominates the motion within this region. The local group spans only a few million light-years, far smaller than a supercluster scale flow, yet still immense beside any scale inside the Milky Way. Within it, the idea of speed becomes more direct. Galaxies move relative to one another through their shared gravitational field. They do not follow perfect circles. Their paths are shaped by mass, distance, past encounters, and the pull of dark matter halos surrounding the larger galaxies. A dark matter halo is a broad, invisible mass envelope inferred from gravity. In the local group, these halos help determine how galaxies approach, orbit, and disturb one another. The Milky Way and Andromeda are the main masses in this region. Observations indicate that Andromeda is moving toward the Milky Way at about 110 kilometers per second along the line of sight. This means the distance between them is decreasing in that direction. Measurements of Andromeda's sideways motion are harder, because even a large speed appears as a tiny shift across the sky at such a great distance. Space telescope observations have improved this measurement. They indicate that Andromeda's sideways motion is small enough that the two large galaxies are likely to interact strongly in the far future. The exact details remain uncertain, because they depend on the masses of both galaxies and their extended halos. Andromeda lies about 2.5 million light-years away. Its light reaches Earth after crossing intergalactic space for a time longer than the history of humans. In that light, Andromeda appears as a broad spiral system with a bright central region, dust lanes, star-forming areas, and many older stars. Yet in the local group, Andromeda is not only an object in the sky, it is a neighbouring mass whose gravity helps define the Milky Way's motion. The two galaxies move around the centre of mass of the local group, a balance point determined mainly by their combined mass. This centre is not a bright object, it is a gravitational reference point. Triangulum also participates in this local motion. It is smaller than the Milky Way and Andromeda, but still much larger than the dwarf galaxies around them. Its relationship with Andromeda is especially important, because it may be gravitationally bound to Andromeda, or may have had past interactions with it. Observations of gas, stars, and motion help astronomers study this relationship. It remains uncertain in detail how Triangulum's past orbit has unfolded, but it clearly belongs to the same local gravitational setting. Around the large galaxies, many dwarf galaxies move on smaller paths. Some are close companions of the Milky Way, such as the Large Magellanic Cloud and the Small Magellanic Cloud. Others are satellites of Andromeda. A dwarf galaxy contains far fewer stars than a large spiral galaxy, but its motion can reveal much about gravity and dark matter. Many dwarf galaxies appear to contain large amounts of dark matter compared with their visible stars. Their speeds around larger galaxies help estimate the mass of the larger halo. Their positions also preserve clues about how the local group formed and evolved. The Large Magellanic Cloud is especially important for the Milky Way's present motion. It is a nearby dwarf galaxy, visible from Earth's southern skies, and it is more massive than many other satellites. Modern measurements indicate that it is likely on its first close passage around the Milky Way, or has not completed many orbits. Its gravity is strong enough to disturb the Milky Way's outer halo and to shift the Milky Way itself slightly. This means the Milky Way is not simply the fixed centre of its own satellite system. It moves in response to its companions, especially the most massive ones. Within the local group, the expansion of space is present as part of the universe, but it does not control the distances between the bound members. Gravity has gathered these galaxies into a shared system. Some smaller galaxies may be falling inward for the first time. Others may have orbited for billions of years. Some may have been stripped of gas by interactions, leaving older stars behind. These details affect local speeds. A satellite galaxy may move at hundreds of kilometers per second relative to the Milky Way, guided by the combined gravity of stars, gas, and dark matter. The local group also contains gas spread between galaxies. Some of this gas is connected to past interactions, especially around the Magellanic Clouds. Long streams of neutral hydrogen extend across the sky, showing that gravity and pressure have pulled gas from smaller galaxies during their motion. These streams are not bright like stars, but radio observations reveal them. They show that motion in the local group is not only the movement of star systems, it also involves gas being stretched, stripped, heated, and sometimes drawn toward larger galaxies. The Milky Way's speed within the local group depends on the chosen frame. Relative to Andromeda, it is approaching along the line between them. Relative to the center of mass of the local group, it has another motion. Relative to its own satellites, it has still more motions, because the Milky Way and its companions pull on one another together. This layered motion is expected in a gravitational system. No galaxy sits absolutely still. Each body responds to the mass around it. The local group is also not sharply separated from all surroundings. Nearby small galaxies and groups lie beyond its main boundary, and some may be only weakly influenced by it. Astronomers estimate membership through distance, velocity, and gravitational binding. In some cases, the classification is clear. In others, it remains uncertain whether a small galaxy belongs to the local group or lies just outside it in the surrounding local volume. This uncertainty is normal at the edges of a gravitational system where motion and distance are both difficult to measure precisely. At this inner cosmic scale, the Milky Way is part of a bound family of galaxies. Its motion is shaped most strongly by Andromeda, by its own satellites, by the shared dark matter environment, and by the history of smaller systems falling inward. The larger universe expands beyond this setting, but inside the local group gravity holds a quieter, closer order. These speeds are still vast by human measures. Yet they belong to a slow gravitational dance across millions of years and millions of light years, where galaxies approach, orbit, disturb, and carry one another through the dark local space. Inside the local group, the Milky Way becomes the main region of motion. Before the bright disk and spiral arms are reached, the galaxy extends outward through a broad halo. This halo is not a sharp shell. It is a wide, faint, uneven region surrounding the visible disk, filled with old stars, globular clusters, thin streams of stellar debris, hot gas, and a much larger amount of dark matter. The halo marks the galaxy's outer gravitational presence. It is part of the Milky Way's body, even though most of it cannot be seen with ordinary sight. The stellar halo contains ancient stars scattered far above and below the disk. Many of these stars are old and metal-poor. In astronomy, metals are elements heavier than hydrogen and helium. Metal-poor stars formed early, before many generations of stars had enriched gas with heavier elements. Their composition preserves information from the young galaxy. Their paths are often stretched and tilted rather than arranged in the flat, circular motion of disk stars. Some move in elongated orbits that carry them far into the halo and then back inward. Their speeds reveal a region shaped by long gravitational history. The Milky Way's halo also contains globular clusters. A globular cluster is a dense, round group of old stars bound together by gravity. These clusters orbit the galaxy at large distances, some above the disk, some below it, and some far out in the halo. They do not all share the same motion. Each cluster follows its own path through the Milky Way's gravitational field. The combined motions of globular clusters help trace the mass of the galaxy, especially where the disk becomes faint and dark matter becomes the dominant gravitational influence. The dark matter halo is the largest part of this region by mass. It does not shine, absorb, or scatter light in a way that telescopes directly detect. Its presence is inferred from gravity. Stars and gas in the Milky Way move faster than would be expected from visible matter alone. Satellite galaxies remain bound at large distances. Stellar streams bend and stretch in ways that reflect the unseen gravitational field. These clues indicate that the Milky Way is embedded in a dark halo much wider than its bright disk. The exact total mass of this halo remains uncertain, because its outer boundary is not sharp and because distant traces are difficult to measure. In the halo, motion is not smooth like the turning of a wheel. It is more like an old record of many arrivals. The Milky Way grew by drawing in smaller galaxies over billions of years. When a smaller galaxy falls into the Milky Way's halo, tides begin to pull it apart. A tide is the difference in gravity across an object. Stars on one side are pulled slightly differently from stars on the other side. Over time, a dwarf galaxy can stretch into a long stream of stars wrapped around the Milky Way. These stellar streams remain visible as faint patterns across the sky, especially in careful surveys that measure position, brightness, colour, and motion. One of the clearest signs of this history is the Sagittarius stream, made of stars stripped from the Sagittarius dwarf galaxy. This stream arcs around the Milky Way, showing that the dwarf has passed through the halo repeatedly while losing stars. Other streams are thinner and fainter, some from disrupted globular clusters, others from small galaxies. Each stream moves along an orbit shaped by the Milky Way's gravitational field. By studying them, astronomers learn how mass is distributed through the halo. The streams are like quiet lines drawn by gravity, showing where smaller systems have been pulled apart. The halo is also affected by the Large Magellanic Cloud. This companion galaxy moves through the Milky Way's outer region with enough mass to disturb the halo. Observations and simulations indicate that it creates a wake, a gravitational response in stars and dark matter behind its path. A wake is a trailing disturbance produced as a massive body moves through a surrounding medium. In this case, the medium is not water or air, but the galaxy's extended halo. The wake changes the motions of halo stars and may help reveal the nature and distribution of dark matter. The hot gas halo forms another part of this outer region. Around the Milky Way lies diffuse gas heated to very high temperatures. It is difficult to observe because it is thin and faint, but it can be detected through its effect on light from more distant objects and through X-ray emission. This gas is connected to the galaxy's supply of matter. Some of it may cool and fall inward over time. Some may be heated by exploding stars, energetic events near the galactic center, or motion through the surrounding environment. Its full structure remains uncertain, but observations indicate that the Milky Way is surrounded by a substantial atmosphere of hot, thin gas. The halo does not rotate as simply as the disk. Some parts may have a mild overall spin, but the motions are mixed. Stars arrive from different directions and at different times. Streams preserve the directions of their parent systems. Satellites move on tilted paths. The halo's motion is therefore a blend of older orbits, recent infall, and the response to massive companions. This makes the halo a region where speed is less orderly, but deeply informative. Every measured motion helps reconstruct the galaxy's mass and past. The outer edge of the Milky Way's halo is not a physical wall. Astronomers may define it by where the galaxy's gravity dominates over other influences, or by a radius enclosing a chosen density contrast. Different definitions give different sizes. The dark matter halo may extend hundreds of thousands of light-years from the galactic center, while some satellite galaxies lie even farther out and may still be bound. The uncertainty is part of the science. Observations indicate a broad dark halo, but its exact mass, shape, and boundary remain active areas of research. Inside this halo, the Milky Way moves as a whole through the local group, yet the halo itself is also alive with internal motion. Old stars cross the dark outskirts. Globular clusters circle through long paths. Dwarf galaxies fall inward or pass through. Streams slowly wrap around the galaxy. Hot gas drifts, heats, cools, and responds to gravity. Dark matter holds the largest unseen structure, shaping the speeds of all the visible traces. The halo is the galaxy's quiet outer field, wide and faint, where the motion of the Milky Way becomes not just a path through space, but a layered system of many smaller motions held within one extended gravitational form. Inside the halo, the Milky Way's bright structure begins to dominate. The galaxy is a rotating spiral system, with most of its visible stars, gas, and dust arranged in a flattened disk around a dense central region. The entire disk turns around the galactic center, carrying the Sun and billions of other stars through space. This rotation is one of the largest motions directly affecting the solar system. It is steady, immense, and continuous across spans of time far beyond human history. The Milky Way does not rotate like a solid wheel. In a solid object, all parts complete a turn together, so the outer edge moves faster because it travels farther in the same amount of time. A galaxy behaves differently. Stars and gas at different distances from the center orbit according to gravity. Inner regions generally complete an orbit more quickly than outer regions. This difference is called differential rotation. It means the galaxy slowly changes its internal pattern over time. Stretching clouds, spiral structures, and streams of stars. The Sun lies far from the galactic center, about 26,000 light-years away. At this distance, the solar system orbits the center at roughly 220 kilometers per second. One full orbit takes about 230 million years. During the entire existence of the human species, the Sun has completed only a tiny fraction of one galactic orbit. Even the dinosaurs lived during a different galactic position from the present one. Yet the motion is too smooth and vast to be sensed directly from Earth. The evidence for galactic rotation comes from many observations. Astronomers measure the motions of stars, clouds of hydrogen gas, and other traces across the galaxy. Radio observations are especially important because radio waves can pass through much of the dust that blocks visible light in the galactic disk. Neutral hydrogen emits radio waves at a characteristic wavelength, allowing astronomers to map motion across large distances. By measuring how this signal shifts in frequency, they determine how different regions move relative to the Sun. These measurements reveal one of the major discoveries of modern astronomy. The outer parts of the Milky Way rotate faster than expected from visible matter alone. If only the observed stars and gas supplied gravity, orbital speeds should decrease strongly with distance from the center. Instead, the rotation curve, a graph of orbital speed against distance, remains relatively flat far from the center. This indicates the presence of additional unseen mass. Dark matter provides the leading explanation. The galaxy's visible disk exists within a much larger dark halo whose gravity keeps outer stars moving rapidly. The spiral arms are part of this rotating system, but they are not rigid structures permanently containing the same stars. Spiral arms are regions of enhanced density, where stars and gas crowd together more strongly. A density wave is one leading explanation for their long-lived pattern. In this view, stars move in and out of the arms while the overall arm pattern persists for extended periods. Gas clouds entering an arm may compress, helping trigger star formation. Bright young stars then illuminate the arm before drifting onward through their own orbits. The rotation of the Milky Way shapes the motion of gas and dust throughout the disk. Vast clouds of hydrogen, molecular gas, and interstellar dust orbit the center along with stars. Some clouds collide or compress. Some form new stars. Some are disturbed by exploding stars called supernovae. These processes occur inside the rotating frame of the galaxy. The motion is therefore not only the orbit of stars, it is also the circulation of gas, the shifting of magnetic fields, and the ongoing recycling of matter through stellar birth and death. Closer to the galactic center, orbital speeds and densities become greater. The central bulge contains many older stars moving in more complex paths than the flatter disk orbits. At the very center lies Sagittarius A star, the supermassive black hole of the Milky Way. Its mass is about 4 million times that of the Sun. Nearby stars orbit it at extremely high speeds, providing strong evidence for its existence. The black hole dominates gravity only within the innermost region. Farther out, the combined mass of stars, gas, and dark matter shapes the galaxy's rotation. The Sun's orbit is not a perfect circle. It moves slightly inward and outward over long periods, while also rising above and below the galactic plane. The galactic plane is the thin average layer where most disk material lies. This vertical motion forms a gentle oscillation through the disk over millions of years. Nearby stars also have their own small differences in speed and direction. The Milky Way is therefore not a perfectly ordered machine. It is a dynamic system where every object follows its own path within the galaxy's gravitational field. The galaxy's rotation affects the appearance of the night sky over long timescales. Constellations slowly change shape because stars move through the galaxy at different speeds and in different directions. Over millions of years, the familiar patterns of the sky dissolve and reform into new arrangements. This change is too slow to notice within one human life without precise instruments, yet it is part of the ongoing galactic motion carrying all nearby stars around the centre. Modern missions such as ESA's Gaia spacecraft have transformed the understanding of these motions. Gaia measures the positions, distances, and motions of vast numbers of stars with extraordinary precision. From these data, astronomers reconstruct streams from disrupted galaxies, identify groups of stars sharing common origins, and map the Milky Way's rotation in detail. The observations show waves, ripples, and asymmetries in stellar motion, indicating that past encounters with dwarf galaxies continue to influence the disk. The Milky Way's rotation is therefore not a simple spin in emptiness. It is the organized motion of a giant gravitational system built from visible matter and dark matter together. The Sun, Earth, and all familiar surroundings move through this galactic orbit continuously, carried at hundreds of kilometers per second around a center hidden behind dense clouds and crowded stars. The movement is calm in experience because everything nearby shares it: oceans, mountains, air. And living bodies all travel together inside the rotating disk, while the galaxy itself continues through the larger motions of the local group and the wider universe beyond. Inside the rotating disk of the Milky Way, the Sun occupies a smaller region known as the Orion Arm, or Orion Spur. This feature is not one of the galaxy's largest spiral arms. It is a shorter structure of stars, gas, and dust located between larger spiral arms. The Sun moves within this local lane as it orbits the galactic center. The region is not a fixed tunnel or a solid band. It is a broad neighborhood of matter, shaped by gravity, star formation, and the differential rotation of the galaxy. The Orion Arm contains bright young stars, older stars, dark clouds of dust, and wide areas of thin gas. It is called an arm because it forms part of the Milky Way's spiral pattern, but its edges are not sharp. Star density changes gradually. Gas clouds gather in some places and thin out in others. The Sun is not at the center of a neat structure. It lies within a local arrangement of stars and clouds that astronomers map by measuring distances, motions, colors, and the light absorbed by dust. This region gives the night sky many of its familiar bright stars. Several nearby constellations contain stars that belong to large associations within the same local arm environment. A stellar association is a loose group of young stars formed from related clouds of gas. These groups are not tightly bound like globular clusters. Over time, their stars drift apart under the influence of galactic rotation and nearby gravitational encounters. Their shared motion still reveals that they formed in common regions of gas. The Orion Arm includes large molecular clouds. A molecular cloud is a cold, dense region of gas where atoms combine into molecules, especially molecular hydrogen. These clouds are among the main birthplaces of stars. Dust mixed with the gas blocks visible light, making some clouds appear as dark shapes against brighter star fields. Inside them, gravity can gather material into denser cores. When a core becomes massive and cold enough, it may collapse and form a new star. This process belongs to the local galactic environment through which the Sun moves, even though the Sun itself is far from the most active parts. The Sun's present surroundings are quieter than many star-forming regions. It lies in a relatively low-density area called the local bubble. This bubble is a cavity in the interstellar medium, the gas and dust between stars. It likely formed from past supernova explosions and strong stellar winds from massive stars. These events cleared and heated the surrounding gas, leaving the Sun inside a thin, hot region compared with denser clouds nearby. the local bubble is not empty. It contains very sparse gas and connects with other cavities and tunnels in the local interstellar environment. Motion within the Orion Arm is layered. The Sun orbits the galactic center with the disk, but nearby stars have slightly different paths. Some move faster, some slower, some inward or outward, and some above or below the galactic plane. The differences are small compared with a full galactic orbit, yet over time they change the local neighborhood completely. A star that is near the Sun now may be far away in a few million years. Another star now unseen to the naked eye may pass closer in the distant future. The local arm is therefore not a permanent gathering of the same stars around the Sun. The Sun also moves relative to the average motion of nearby stars. This is called the Sun's peculiar motion with respect to the local standard of rest. The local standard of rest is an idealized reference frame based on the average circular motion of matter near the Sun's position in the galaxy. Against that frame, the Sun has a modest additional motion, measured in kilometers per second. It drifts in a particular direction through the local stellar neighborhood, while also sharing the much faster orbit around the galactic center. The Orion Arm itself is difficult to map from within. Earth lies inside the Milky Way's disk, surrounded by dust and stars. From this position, the galaxy cannot be seen from outside as a full spiral. Astronomers build the map from distance measurements, radio emission from gas, young star positions, masses, and stellar motions. A massa is a natural source of amplified microwave radiation, often found in star-forming regions. These sources can be measured with great precision using radio telescopes across Earth. Their motions help trace the shape of nearby spiral features. The mapping shows that the Orion Arm is a real local structure, not merely a visual accident. It contains organized star-forming regions and gas clouds extending for thousands of light years. Still, its exact shape and connection to larger spiral arms remain active subjects of study. Observations indicate a coherent local spur or arm segment. It remains uncertain how long-lived this structure is and how it connects dynamically to the broader spiral pattern of the galaxy. In this region, speed can be understood through the changing relationships among nearby stars and clouds. The Sun is not ploughing through dense matter like a ship through water. Interstellar space is extremely thin. Even the denser clouds are far emptier than the best vacuums made in laboratories on Earth. Yet the motion is real. The Sun passes through different interstellar environments over millions of years. The surrounding gas pressure, dust density, and magnetic field can vary as the solar system moves from one region to another within the local arm. Some nearby stars share a common origin or motion, forming moving groups. A moving group is a set of stars with similar paths through the galaxy. Some are remnants of old clusters that have dispersed. Others may be shaped by resonances and gravitational influences in the Milky Way's disk. These shared motions show that the local neighborhood is structured, not random. The stars around the Sun carry traces of birthplaces, encounters, and the wider rotation of the galaxy. The Orion Arm also contains dust that affects how the universe is seen from Earth. Dust grains absorb and scatter starlight, especially blue light, making distant stars appear dimmer and redder. This dust lies in clouds and sheets across the local arm. It hides some regions and outlines others. Mapping dust helps astronomers understand both the structure of the arm and the limits of observation from within it. The same material that dims the view also marks where gas has gathered and where stars may form. Within this local spiral lane, the Sun's great speed around the galaxy becomes part of a smaller and quieter neighborhood. It travels among stars that drift on their own paths, through a thin medium shaped by old explosions and new star formation. The Orion Arm is not still, not fixed and not sharply bounded. It is a living part of the Milky Way's disk, where the sun moves within a changing pattern of gas, dust, young stars, old stars, and faint magnetic fields. This is the galaxy at a nearer scale, no longer only a rotating disk, but a local road of light and matter carrying the solar system through its long orbit. Inside the Orion Arm, the sun belongs to a nearer and more changeable neighborhood of stars. These stars are spread through space at distances measured in light years, each following its own path around the Milky Way. From Earth, they appear fixed in familiar patterns because they are so far away, and because human lifetimes are short. In reality, every star moves. The local sky is a temporary arrangement, a quiet crossing of many separate orbits within the galaxy's disk. The nearest star system to the Sun is Alpha Centauri. It is a group of 3 stars, including Proxima Centauri, the closest known star beyond the Sun. Proxima is a small red dwarf, faint and cool compared with the Sun. The 2 brighter Alpha Centauri stars orbit each other, while Proxima is more distant from them and gravitationally linked on a wider path. This nearby system moves through space relative to the Sun, and its distance changes slowly with time. It is close in galactic terms. Yet its light still takes more than 4 years to reach Earth. Nearby stars are measured through parallax, the slight apparent shift of a star's position as Earth moves around the Sun. Parallax means viewing an object from 2 different positions and measuring the change in apparent direction. For stars, this shift is tiny, but it can reveal distance with great precision. ESA's Gaia spacecraft has measured parallaxes and motions for huge numbers of stars, giving a detailed map of the local stellar environment. The map shows that the Sun is surrounded by stars of many ages, masses, colors, and speeds. Most nearby stars are red dwarfs. These stars are smaller, cooler, and dimmer than the Sun. They burn their nuclear fuel slowly and can last for extremely long times. Because they are faint, many nearby red dwarfs cannot be seen without telescopes. The bright stars visible in the night sky are often not the closest ones. They are seen because they are large, luminous, or young. The true local population is quieter, filled mostly with small stars that shine weakly and move steadily through the galactic disk. The motion of each nearby star is described by 2 main parts. One part is radial motion, movement toward or away from the Sun, measured through shifts in the star's light. The other part is proper motion, movement across the sky, measured as a slow change in position. Together with distance, these measurements give the stars 3-dimensional velocity through space. This velocity is not measured against an absolute stillness. It is measured relative to the Sun, to the local standard of rest, or to other chosen frames. Some stars pass relatively close to the Sun over long spans of time. A close stellar passage does not usually mean danger. Space between stars is vast, and even a close passage by astronomical standards may be many thousands of times farther away than the distance from Earth to the Sun. Still, such passages can gently disturb the far outer cloud of icy bodies surrounding the solar system. Observations and orbital calculations identify stars that passed near the Sun in the past, or may pass near it in the future. The details remain uncertain for faint stars and for very long times, because small measurement errors grow larger when paths are projected across millions of years. The local neighborhood includes stellar streams and moving groups. These are sets of stars with related motion. Some moving groups may be the remains of star clusters that form together and slowly spread apart. Others may be shaped by the gravitational pattern of the Milky Way, including spiral arms and the central bar. A central bar is an elongated structure of stars in the inner galaxy that affects orbits throughout the disk, near the Sun. These shared motions appear as subtle groupings in velocity space, a map not of position alone but of how stars move. Open clusters also pass through the wider nearby region. An open cluster is a loose group of stars formed from the same cloud. Over time, encounters with gas clouds, the galaxy's tide, and the different orbital speeds of stars pull clusters apart. Some nearby stars may once have belonged to clusters that are now dispersed. The Sun itself likely formed in a cluster or association, because most stars form in groups. Its birth companions are now scattered through the Milky Way, and their exact identities remain uncertain. The Sun's motion relative to nearby stars creates a direction called the solar apex. This is the direction in the sky toward which the Sun moves compared with the average motion of nearby stars. The opposite direction is where the Sun appears to move away. This does not mean the Sun has a destination among those stars. It means that in the local frame, the Sun's path has a measurable direction. Nearby stars, seen over long times, would appear to drift outward from one region of the sky and inward toward another because of this relative motion. The speeds involved are modest compared with the Sun's orbit around the galactic center, yet they are still large by ordinary measures. Nearby stars often move at tens of kilometers per second relative to the Sun. Over 1 million years. Even such a speed carries a star across many light years. This means the solar neighborhood is continually replaced. The stars closest to the Sun now were not the closest in the distant past, and will not remain the closest in the distant future. The local sky is a flowing pattern rather than a fixed arrangement. Interstellar space between these stars is not empty. It contains very thin gas, dust grains, magnetic fields, and energetic particles. Stars move through this medium while also producing winds of charged particles. Massive stars can shape large cavities with strong winds and supernova explosions. Smaller stars create smaller surrounding bubbles. The Sun's own bubble sits within this shared environment, but at the scale of nearby stars, many such bubbles and clouds overlap in a broad, sparse medium. The motion of nearby stars also helps reveal the mass distribution of the Milky Way near the Sun. Stars moving above and below the galactic plane respond to the gravity of the disk. By measuring their vertical motions, astronomers estimate the amount of matter in the local disk, including stars, gas, and dark matter. These measurements support the broader picture that dark matter contributes to the galaxy's gravity. Although ordinary matter dominates some local details close to the disk, at this scale, the Sun is one star among many, neither still nor isolated. It travels through a changing neighborhood where faint red dwarfs, bright young stars, stellar remnants, clusters, and streams all follow separate paths. Their motions are measured by small shifts in light and position, then assembled into a living map of the local galaxy. The familiar constellations are only a present pattern on this moving field. Beneath their calm appearance, every star drifts, and the Sun drifts with them, carried by the galaxy while also moving through its own near company of passing lights. Inside the neighborhood of nearby stars, the Sun surrounds itself with a moving boundary called the heliosphere. This region is formed by the solar wind, a steady flow of charged particles streaming outward from the Sun. The solar wind is mostly protons and electrons, with smaller amounts of heavier particles. It carries the Sun's magnetic field outward through space. As it expands, it meets the thin gas, dust, magnetic fields, and charged particles of the local interstellar medium. The meeting between these two environments creates a large, uneven bubble around the solar system. The heliosphere is not a hard shell. It is a region of influence, shaped by pressure and motion. Near the Sun, the solar wind flows outward at hundreds of kilometers per second. Farther away, it spreads thinner and weaker. Eventually, it slows where the pressure of the interstellar medium becomes important. This slowing region is called the termination shock. A shock is a sudden change in speed, pressure, and temperature in a flowing gas or plasma. Plasma is gas whose particles are electrically charged. Beyond this slowing region lies a broad outer zone called the heliosheath, where solar wind particles are heated, compressed, and disturbed. The outer boundary of the heliosphere is called the heliopause. At the heliopause, the outward pressure of the solar wind balances the pressure of the interstellar medium. This boundary shifts because the solar wind changes with the Sun's activity, and because the surrounding interstellar environment is not perfectly uniform. The heliopause is not a perfect sphere. It is shaped by the Sun's motion through the local interstellar gas and by magnetic fields on both sides. Observations from spacecraft indicate that the boundary is complex, with changing flows and particle populations rather than a smooth, simple edge. The Sun moves through the local interstellar medium at several tens of kilometers per second relative to the nearby gas. Because of this motion, the heliosphere has a direction of travel. The forward side faces the incoming interstellar flow. The opposite side trails behind. Older models often pictured a long comet-like tail. Newer observations suggest a more rounded or partly shortened shape, influenced strongly by magnetic fields. It remains uncertain exactly how far the heliosphere extends behind the Sun, because direct measurements are limited and the outer region is difficult to observe from within. 2 spacecraft have crossed the heliopause. Voyager 1 and Voyager 2 were launched by NASA in the late 1970s and later travelled beyond the planets. Voyager 1 crossed into interstellar space in 2012, and Voyager 2 crossed in 2018. Their instruments measured changes in particles and magnetic fields that mark the transition away from the solar wind-dominated region. These crossings confirmed that the heliosphere has a real boundary, though one that is broad, active, and shaped by changing conditions. The heliosphere moves with the Sun around the Milky Way. It is carried through the local interstellar medium like a bubble around a moving star. This motion affects how interstellar particles enter the solar system. Neutral atoms, which have no electric charge, can pass more easily through magnetic barriers. Charged particles are guided and deflected by magnetic fields. Dust grains also enter, though their paths depend on size, charge, and radiation pressure from sunlight. The heliosphere filters part of the surrounding galaxy before it reaches the inner solar system. Cosmic rays are an important part of this boundary story. Galactic cosmic rays are high-energy particles that arrive from outside the solar system, many from distant explosive or energetic processes in the Milky Way. The heliosphere reduces the number of lower-energy cosmic rays that reach the planets. This shielding changes with the solar cycle, the roughly 11-year rise and fall of solar magnetic activity. During stronger solar activity, the Sun's magnetic field becomes more disturbed and can block more incoming cosmic rays. During quieter periods, more cosmic rays can enter. The shielding is not complete, but it is significant. The heliosphere also changes when the Sun releases bursts of material called coronal mass ejections. These eruptions send clouds of magnetized plasma outward. Near Earth, they can disturb the planet's magnetic field and create geomagnetic storms. Farther out, they travel through the solar wind and can eventually affect the structure of the outer heliosphere. The bubble around the solar system is therefore not steady in every detail. It breathes with the sun's activity, expanding and contracting in response to changing pressure. The interstellar medium around the heliosphere is extremely thin. Even so, it matters because the heliosphere is so large and the solar wind becomes weak at great distance. The sun currently lies in a small flow of warm, partly ionized interstellar material. Ionized means that some atoms have lost electrons and become charged. This local cloud is part of the wider environment inside the local bubble. Observations of nearby stars and interstellar atoms entering the solar system help describe this surrounding material. Its density, temperature, and magnetic field are measured with uncertainty, because the cloud is faint and spread thinly across space. The heliosphere is connected to speed in a quiet but direct way. It exists because the sun emits an outward wind while also moving through surrounding galactic material. Without the solar wind, the planets will be more exposed to interstellar plasma and cosmic rays. Without the surrounding medium, the solar wind would not form the same outer boundary. The shape is the result of motion, pressure, magnetic fields, and particles meeting across a vast distance. The planets orbit well inside the heliosphere. Even the farthest known planetary region lies deep within the sun's protective influence compared with the heliopause. The boundary crossed by the Voyager spacecraft is far beyond the orbit of Neptune. It is measured in astronomical units, where one astronomical unit is the average distance between Earth and the Sun, in written full scale. The heliopause lies more than 100 astronomical units from the Sun, in the directions where Voyager travelled. The exact distance changes with direction and time. Inside this bubble, the solar system is not exposed directly to interstellar space in its raw form. It travels inside a moving solar atmosphere extended far beyond the planets. The sun's wind fills the region, its magnetic field spirals outward, and particles from the galaxy press gently from outside. The heliosphere is the sun's outer weather, stretched into interstellar space and shaped by the star's journey through the local arm. It marks a nearer layer of cosmic speed, where the motion of a star through thin galactic gas becomes a boundary that surrounds every planet, every comet, and every quiet orbit held within the solar system. Inside the heliosphere, the solar system forms a flatter and more orderly region of motion. The planets, dwarf planets, asteroids, comets, dust, and smaller bodies mostly orbit the Sun within a shared plane called the ecliptic plane. This arrangement comes from the solar system's formation. Long ago, the Sun and planets emerged from a rotating cloud of gas and dust. As gravity pulled the cloud inward, conservation of angular momentum caused the material to spin faster and flatten into a disk. Angular momentum is the tendency of a rotating system to keep rotating. From that ancient disk, the planets formed and inherited a common direction of motion. Most planets orbit the Sun in the same direction. Their paths are close to the ecliptic plane, though not perfectly aligned. Mercury has a more tilted orbit than most planets, and some dwarf planets and comets follow highly inclined paths. Even so, the overall system preserves the shape of the original rotating disk. This shared movement gives the solar system a calm structural order inside the wider and more varied motions of the galaxy. The Sun contains almost all the mass in the solar system. Its gravity dominates the motions of the planets. Each planet follows an orbit determined mainly by the Sun's pull, though the planets also affect one another slightly through their own gravity. These mutual influences slowly change orbital shapes and orientations over long periods. The solar system is stable across immense spans of time, but it is not perfectly fixed. Every orbit shifts gradually. The planets do not travel in perfect circles. Their orbits are ellipse, meaning slightly stretched circles. Some, like Earth, have nearly circular paths. Others, such as Mercury, show more noticeable elongation. A planet moves faster when closer to the Sun and slower when farther away. This variation follows the conservation of angular momentum within gravity. The changing speed is smooth and continuous, with no sudden stop or push required to keep the planets moving in space. Motion continues naturally unless altered by forces such as gravity. The planets also orbit in different time periods. Mercury completes an orbit in only about 88 days. Neptune takes about 165 years. The farther a planet lies from the Sun, the larger its orbit and the slower its average orbital speed. Inner planets move quickly through smaller paths. Outer planets move more slowly through vast cold distances, yet all remain linked within the same rotating system around the Sun. Asteroids share this broad orbital order. Most lie in the asteroid belt between Mars and Jupiter. These rocky bodies orbit in the same general direction as the planets, though with a wider range of orbital tilts and shapes. Jupiter's gravity strongly affects the belt. Certain orbital regions become unstable because repeated gravitational interactions disturb asteroids over time. These gaps are called Kirkwood gaps. Some asteroids are shifted into new paths, occasionally crossing the orbits of planets. Comets introduce a more varied pattern. Short-period comets usually come from the Kuiper belt beyond Neptune and often orbit near the ecliptic plane. Long-period comets arrive from the distant Oort cloud, a broad spherical region of icy bodies surrounding the solar system. These comets can approach from almost any direction, showing that the outermost solar system is less flat and more scattered than the planetary region. When a comet falls inward toward the Sun, heat releases gas and dust, forming glowing tails pushed by sunlight and the solar wind. The giant planets strongly shape the motion of smaller bodies. Jupiter, the most massive planet, acts as a major gravitational influence throughout the solar system. Its gravity can redirect comets, disturb asteroid orbits, and help stabilize or destabilize smaller objects depending on the situation. Saturn, Uranus, and Neptune also contribute to this long gravitational pattern. Their combined effects create resonances, regions where orbital periods form repeating ratios. A resonance means that objects repeatedly align in similar positions, allowing gravity to build cumulative effects over time. The planets themselves carry systems of moons. Many moons orbit in the same direction as their parent planets rotate, reflecting their formation from local disks around young planets. Other moons were likely captured later and follow more tilted or reversed paths. The motion inside the solar system therefore repeats similar patterns at smaller scales. Rotating disks produce shared directions of movement, while captures and collisions add irregularity. Dust also moves through the solar system. Tiny grains from comets, asteroids, and collisions orbit the Sun in vast numbers. Sunlight and the solar wind gradually alter their paths. Some spiral slowly inward toward the Sun. Others are pushed outward or scattered by planets. This dust reflects sunlight and creates faint structures such as the zodiacal light, a dim glow sometimes visible before sunrise or after sunset under dark skies. The solar system is therefore not empty between planets. It contains a thin, moving haze of small particles crossing space. The solar system's plane itself is tilted relative to the Milky Way. The planets do not orbit within the galactic plane. Instead, the entire solar system moves through the galaxy with its own orientation, carried by the Sun around the galactic center. This means that planetary motion and galactic motion overlap without needing to align. Earth circles the Sun while the Sun circles the galaxy, and while the galaxy moves through the local group. None of these motions cancels the others. They combine continuously. Spacecraft traveling through the solar system must account for these layered motions. A mission to another planet is not launched toward a stationary target. Both Earth and the destination planet move around the Sun during the journey. Engineers calculate transfer paths that intercept the future position of the target world. Some missions use gravitational assists, gaining or losing speed by passing near planets. In these maneuvers, motion and gravity exchange energy in predictable ways inside the larger orbital system. The solar system's shared plane creates a sense of order because most major bodies move together in one broad direction around the Sun. This order is ancient, preserved from the rotating cloud that formed the planets billions of years ago. Yet within that calm arrangement, every object follows its own exact path. Planets shift in speed along elliptical orbits. Asteroids drift under resonances. Comets dive inward from deep cold regions. Dust spirals through sunlight. Moons circle planets while planets circle the Sun. The entire structure travels together inside the heliosphere, carrying its layered motions quietly through the wider galaxy. Inside the shared plane of the solar system, Earth follows its own yearly path around the Sun. This motion is one of the most important speeds connected to ordinary life, although it is not felt as a rush. Earth moves around the Sun at an average speed of about 107,000 kilometers per hour. The planet is carried along by gravity and inertia. Inertia is the tendency of an object to keep moving unless a force changes its motion. Gravity bends Earth's path inward, while inertia carries it forward, and the result is a steady orbit. Earth's orbit is not a perfect circle. It is a slight ellipse, with the Sun placed a little away from the centre. At one part of the orbit, Earth is closest to the Sun. This point is called perihelion. At another part, Earth is farthest from the Sun. This point is called aphelion. The distance difference is real, but it is not the main cause of the seasons. Seasons come mostly from the tilt of Earth's axis. The orbit changes Earth's speed gently, making it move a little faster near perihelion and a little slower near aphelion. The average distance from Earth to the Sun is called 1 astronomical unit. Written in full distance, it is about 150 million kilometers. Light from the Sun crosses this distance in a little over 8 minutes. Earth therefore orbits within sunlight that left the solar surface minutes earlier. The light warms the planet, drives weather, feeds photosynthesis, and marks the rhythm of day and year. The motion around the Sun gives the year its length. About 365 days, with a small extra fraction that leads to leap years in the calendar. The orbital path is smooth because space offers almost no resistance. Earth does not need a constant forward push to keep moving. Once set in motion during the formation of the solar system, it continues along its orbit while gravity continually changes the direction of its velocity. Velocity means speed together with direction. Earth's speed remains close to the same value through the year, but the direction of motion changes at every moment. This changing direction is the curve of the orbit. The Sun also moves slightly in response to Earth. Earth does not orbit the exact center of the Sun. Instead, both Earth and the Sun move around their shared center of mass. Because the Sun is far more massive, this shared center lies deep inside the Sun. The motion is small, but it is part of the same gravitational truth. Every planet pulls on the Sun. Jupiter produces the largest solar wobble because of its great mass. Earth's contribution is smaller, but not absent. The solar system is a set of bodies moving around common centers of mass. not a single fixed sun with passive objects circling it. Earth's orbit is influenced by the other planets. Their gravity causes slow changes in the shape and orientation of Earth's path. These changes occur over thousands to hundreds of thousands of years. They include variations in orbital eccentricity, which is the degree of stretching in an orbit, and changes in the direction of Earth's closest approach to the Sun, together with changes in axial tilt and wobble. These orbital variations affect long-term climate patterns. They do not replace the role of greenhouse gases in modern climate change, but they are important in natural ice age cycles over geological time. The Moon travels with Earth around the Sun while also orbiting Earth. The Earth-Moon system moves around a shared centre of mass located inside Earth, but not at its centre. As Earth follows its solar orbit, the Moon's path around the Sun is always drawn forward by the strong pull of the Sun, with gentle waves caused by its orbit around Earth. This shared motion means Earth is not alone on its path. It carries a large companion, tides, and a shifting balance of gravity through the year. Earth's orbital motion also changes the view of the stars. Over the year, the night side of Earth faces different directions in space. This makes different constellations visible in different seasons. The changing view is not caused by stars moving rapidly around Earth. It comes from Earth's changing position around the Sun. The same yearly motion allows parallax measurements of nearby stars, because Earth observes them from opposite sides of its orbit at different times of year. This small shift reveals stellar distances and connects Earth's local motion to the mapping of nearby space. The planet's orbital speed is shared by everything gravitationally bound to Earth: oceans, mountains, the atmosphere, spacecraft in Earth orbit, and living bodies all travel around the Sun together. Because the motion is shared, it does not create a constant wind or pressure that can be felt at the surface. Motion is usually sensed through acceleration, vibration, or changing speed relative to nearby surroundings. Earth's solar orbit is smooth, and the nearby surroundings share it. The speed is immense, but the experience is quiet. The orbit also defines the flow of solar energy across the planet. The tilt of Earth's axis causes one hemisphere to lean more toward the Sun during part of the year and away during another part. This changes the height of the Sun in the sky and the length of daylight. The orbital motion carries the tilted planet through these changing orientations. The result is the annual cycle of seasons, strongest away from the equator and gentler near it. The speed around the Sun is therefore linked not only to position in space, but also to the slow pattern of light and temperature on the surface. Earth's path around the Sun is stable but not perfectly permanent. Over the lifetime of the solar system, gravitational interactions, solar evolution, and rare close passages of other stars can alter conditions. On present timescales, the orbit is well described and highly predictable. Observations indicate no sudden change in Earth's orbital motion. The small variations that do occur are measured and included in precise models of planetary motion. At this inner solar scale, Earth is a moving world held in a steady curve by the Sun's gravity. It travels fast enough to cross its own diameter in only minutes, yet every sea, stone, cloud, and organism shares the same path. The orbital motion does not feel like speed because it is common to the whole planet and its surroundings. It appears instead as the year, as seasonal light, as the changing night sky, and as the quiet geometry by which Earth remains near the Sun while never falling straight inward. Inside Earth's yearly orbit, the planet turns on its own axis. This rotation creates the cycle of day and night, and adds another layer to the many speeds already carrying Earth through space. The rotation is steady and ancient. Earth spins from west to east, causing the sun, moon, planets, and stars to appear to rise in the east and set in the west. This apparent motion belongs mainly to the turning of Earth rather than to the movement of the sky itself. One full rotation relative to the distant stars takes about 23 hours and 56 minutes. This interval is called a sidereal day. A solar day, measured from one noon to the next, is slightly longer because Earth also moves along its orbit around the Sun during each rotation. The difference is small but important in astronomy and timekeeping. The rotating Earth must turn a little farther each day for the Sun to return to the same position in the sky. The speed of Earth's rotation depends on latitude. Latitude measures position north or south of the equator. At the equator, a person travels the greatest distance during one rotation because the equator forms the widest circle around Earth. Near the poles, the circle becomes much smaller. At the poles themselves, the rotation carries a person around a tiny circle in place. The equatorial surface speed is about 1,670 kilometers per hour. This is far slower than Earth's orbital motion around the Sun, yet still much faster than most ordinary travel on the surface. The rotation exists because the cloud of material that formed Earth already possessed angular momentum. As the young planet gathered matter, collisions and gravity shaped it into a spinning sphere. Large impacts during the early solar system altered the speed and tilt of that rotation. One giant collision, thought to involve a Mars-sized body, likely contributed to the formation of the Moon and helped set Earth's present axial tilt. Observations and simulations support this broad picture, though details of the impact remain uncertain. Earth's rotation is gradually slowing. The change is extremely small over one human lifetime, but over millions of years it becomes measurable. The main cause is tidal interaction with the Moon. Earth's rotation raises tidal bulges in the oceans and, to a smaller degree, in the solid planet itself. Because Earth rotates faster than the Moon orbits, the tidal bulges are carried slightly ahead of the Earth-Moon line. The Moon's gravity pulls on these bulges, slowing Earth's rotation while transferring angular momentum outward. As a result, the Moon slowly moves farther away from Earth. Evidence for this slowing comes from precise measurements and from ancient geological records. Some rock formations preserve patterns linked to tides and day length hundreds of millions of years ago. These records indicate that Earth once rotated faster and days were shorter. In the distant past, a day may have lasted only about 22 hours or even less. The slowing continues today at a rate measured in milliseconds per century. Earth's rotation is not perfectly steady in every detail. Small changes occur because mass shifts within and upon the planet. Movements in the atmosphere, oceans, glaciers, and molten outer core can alter the distribution of mass and slightly affect the rotation rate. Large earthquakes can also shift mass enough to produce tiny measurable changes in Earth's spin. These changes are extremely small, detectable mainly through sensitive instruments and precise timekeeping systems. The rotating Earth is slightly flattened at the poles and wider at the equator. This shape is called an oblate spheroid. The flattening occurs because rotation creates an outward effect strongest at the equator. Gravity still dominates, holding the planet together, but the rotation changes the shape slightly. The equatorial radius is therefore larger than the polar radius by several tens of kilometers. This difference influences gravity, satellite orbits, and ocean shape. Rotation also creates the Coriolis effect, an apparent deflection of moving objects within a rotating frame. In the northern hemisphere, large-scale motions tend to curve to the right. In the southern hemisphere, they tend to curve to the left. The Coriolis effect does not cause motion by itself. It alters the paths of moving air, ocean currents, and long-range projectiles because Earth rotates beneath them. This effect helps shape global wind patterns and the rotation of large weather systems. At the poles, rotation produces unusual patterns of light and darkness through the year. During part of the year, one pole remains turned toward the sun, creating continuous daylight. During another part, it turns away, creating continuous darkness. These long polar days and nights arise from the combination of the Earth's rotation and axial tilt during its orbit around the sun. Near the equator, day and night remain more even through the year. The rotation axis itself slowly changes direction in space through a motion called precession. Precession is a gradual wobble in the orientation of the axis, caused mainly by gravitational forces from the Moon and Sun acting on Earth's equatorial bulge. One full cycle takes about 26,000 years. This means the pole star changes over long periods. Today Polaris lies near the north celestial pole, but thousands of years ago different stars held that position, and different stars will hold it in the future. Spacecraft and satellites must account for Earth's rotation. A launch toward the east gains additional speed from the turning planet. Launch sites near the equator receive the greatest benefit because equatorial rotational speed is highest. Earth's rotation also affects navigation systems, communications, and the tracking of objects in orbit. Even the operation of large telescopes depends on precise knowledge of the planet's rotation and orientation. To those standing on the surface, Earth's rotation feels still because everything nearby shares it. Buildings, seas, clouds, and bodies move together with the planet. The turning becomes visible mainly through changing shadows, shifting stars, and the rhythm of daylight. Beneath that familiar calm, every point on the surface traces a circular path through space each day. At the equator, the ground moves faster than the speed of sound in air, though no rushing sensation accompanies it. Earth turns quietly inside its orbit, carrying every mountain, forest, ocean, and city through another layer of cosmic motion that has continued for billions of years. Inside Earth's rotation, the atmosphere forms a moving layer of air that turns with the planet while also flowing through its own patterns. It is held near the surface by gravity and carried around Earth by the same rotation that moves oceans, land, and living things. The air does not lag behind in a simple way, because it has been part of the rotating planet for a very long time. It shares Earth's spin, yet it also moves relative to the ground as wind. This makes the atmosphere a region where shared motion and local motion exist together. The atmosphere is made mostly of nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, water vapor, and trace gases. Near the surface, air is densest because the weight of the air above compresses it. Higher up, the air becomes thinner. The lowest major layer is the troposphere, where most weather occurs. It contains clouds, rain, snow, storms, and much of the water vapor. The top of the troposphere is not at one fixed height. It is higher in the tropics and lower near the poles, changing with temperature and season. The atmosphere rotates with Earth, but not as a rigid shell. Different regions move at different speeds relative to the surface. Winds form because pressure, temperature, gravity, and rotation interact. Air moves from areas of higher pressure toward areas of lower pressure. But the Coriolis effect curves its path. Near the ground, friction with the surface slows the wind and changes its direction. Higher in the atmosphere, where friction is weaker, winds can flow faster and more freely around pressure systems. Sunlight drives much of this motion. The equator receives more direct solar energy than the poles. Warm air near the tropics tends to rise, while cooler air at higher latitudes tends to sink. This uneven heating creates large circulation cells. A circulation cell is a broad loop of rising, flowing, sinking, and returning air. Earth's rotation divides the circulation into several bands rather than one simple flow from equator to pole. The result is a pattern of trade winds, westerlies, polar easterlies, and shifting storm tracks. Near the equator, warm air rises in a broad zone where surface winds often converge. As the air rises, it cools, and water vapor condenses into clouds and rain. Higher above, some of the air flows away from the equator and later sinks in subtropical regions. This sinking air helps create many of the Earth's dry desert belts. At the surface, air returns toward the equator as trade winds. The trade winds do not blow straight north or south, because Earth's rotation curves them. They become easterly winds, moving from the east toward the west in the tropics. At middle latitudes, the prevailing winds often move from west to east. These westerlies guide many weather systems across oceans and continents. They are linked to contrast between warm and cold air, especially along zones where air masses meet. When strong temperature differences develop, waves form in the atmosphere. These waves can grow into low-pressure systems with clouds, wind, and precipitation. The movement of these systems reflects both the flow of air and the turning of Earth beneath it. High above the surface, narrow bands of strong wind called jet streams circle parts of the planet. A jet stream forms where strong temperature differences create strong pressure differences at altitude. The polar jet stream, often found between colder polar air and warmer mid-latitude air, can guide storms and influence weather patterns. Jet streams do not flow in perfect circles. They bend north and south in large waves. Their positions shift with seasons and with changes in the atmosphere below. The atmosphere also contains vertical motion. Air rises in storms, mountain waves, and heated regions over land. Air sinks in high-pressure areas and in the dry centers of circulation cells. Rising air cools as pressure decreases with height. If it contains enough water vapor, clouds form. Sinking air warms as pressure increases, often clearing clouds. These vertical movements are slower than many horizontal winds, but they are essential to weather and climate. The surface of Earth strongly shapes atmospheric motion. Oceans heat and cool more slowly than land. Mountains force air upward, creating clouds and precipitation on one side and drier air on the other. Forests, ice sheets, cities, deserts, and fields all exchange heat, moisture, and momentum with the air above them. Momentum is motion carried by mass. Through friction and turbulence, the surface slows the lowest winds and mixes air in the boundary layer. The part of the atmosphere directly influenced by the ground. Water vapor adds another layer of motion and energy. When water evaporates from oceans, lakes, soil, or plants, it enters the air as vapor. When it condenses into droplets or ice crystals, it releases heat. This heat can strengthen storms and shape tropical cyclones. A tropical cyclone is a rotating storm system powered by warm ocean water and organized by Earth's rotation. Such storms draw energy from the ocean surface, develop deep clouds, and move within the larger atmospheric flow. Their rotation is another visible expression of moving air on a turning planet. The atmosphere does not end suddenly. Above the troposphere lies the stratosphere, which contains the ozone layer. Ozone absorbs much of the sun's harmful ultraviolet radiation and warms the stratosphere with height. Higher still are thinner layers where air becomes increasingly sparse. At great altitude, particles can travel long distances before colliding. The upper atmosphere responds to sunlight, solar storms, and Earth's magnetic field. It expands and contracts with solar activity, affecting the drag on low-orbiting satellites. Even though the atmosphere shares Earth's rotation, it can exchange angular momentum with the solid planet. Changes in global winds can produce tiny changes in Earth's rotation rate. These effects are small but measurable. The atmosphere is therefore not just carried passively. It is part of a coupled system with oceans, ice, land, and the solid Earth. Motion passes between them through pressure, friction, gravity, and heat. At this scale, speed becomes familiar as wind, yet it remains connected to the planet's larger movements. Air circles Earth with the rotating surface, flows between pressure regions, rises and sinks through changing layers, and bends under the Coriolis effect. A calm day near the ground does not mean stillness. The air remains part of a rotating world, an orbiting planet, a moving solar system, and a galaxy in motion. The atmosphere is a thin, restless covering, held by gravity and shaped by sunlight, where the speed of Earth becomes weather, clouds, and the slow breathing of the sky. Inside the moving atmosphere, Earth's oceans and solid crust form the heavier surface layers of the planet. They share Earth's rotation and orbit around the Sun, yet they also move in their own slower and deeper ways. The oceans flow across basins, the crust shifts on plates, tides rise and fall under the pull of the moon and sun. These motions are small compared with orbital and galactic speeds, but they shape the world most directly, changing shores, mountains, currents, and the floor beneath the sea. The oceans cover most of Earth's surface. They are carried around the planet by rotation, held down by gravity, and stirred by wind, heat, salt, tides, and Earth's shape. At the surface, winds push water into broad currents. The Coriolis effect bends these currents, helping form large rotating systems called gyres. A gyre is a wide circular pattern of ocean flow. In the North Atlantic, for example, currents move in a clockwise pattern, while in the South Atlantic they move counterclockwise. These directions reflect Earth's rotation and the arrangement of continents. Surface currents carry heat across the planet. Warm water from low latitudes moves toward higher latitudes, and cooler water returns by other paths. This movement affects climate by redistributing energy from the sun. The Gulf Stream and its extensions carry warm water through the North Atlantic, influencing nearby weather and temperature. Other currents flow along the edges of continents or across open ocean basins. Their speeds are much slower than Earth's rotation through space. But their influence is large because water stores and transports heat so effectively. Below the surface, the oceans move through a deeper circulation driven by temperature and salinity. Salinity means the amount of dissolved salt in seawater. Cold, salty water is denser than warm or fresher water, so it can sink in high latitude regions. This sinking helps drive a global pattern sometimes called overturning circulation, where deep water moves through ocean basins and eventually rises again. The full circulation takes hundreds to more than 1,000 years to complete. It is not a single simple belt, but a connected system of deep and shallow flows shaped by density, winds, seafloor ridges, and mixing. Tides add another rhythm. The moon's gravity pulls more strongly on the side of Earth facing the moon and less strongly on the far side. This difference creates tidal bulges in the oceans. The sun also contributes to tides, though the moon has the stronger tidal effect on Earth. As Earth rotates, coastlines pass through these tidal patterns and sea level rises and falls. The shape of ocean basins, continental shelves, and coastlines can amplify or reduce tides locally. In some places the tide is small, in others it becomes a large daily movement of water. Tides also move through the solid Earth. The crust rises and falls slightly under lunar and solar gravity, a motion called solid Earth tide. This movement is usually measured in centimeters, not in waves visible to the eye. It shows that the ground is not perfectly rigid. Earth responds elastically to gravitational forces, bending slightly and returning. The oceans, atmosphere, and crust all participate in the tidal exchange of energy and angular momentum between Earth and the Moon. The crust itself is divided into tectonic plates. These plates are pieces of Earth's outer shell, including crust and the uppermost mantle. They move slowly across the planet, usually at rates of centimeters per year. This is about the speed at which fingernails grow. Yet across millions of years it opens oceans, closes seas, raises mountains, and moves continents. Plate motion is driven by heat escaping from Earth's interior, gravity acting on cold sinking slabs, and the slow flow of the mantle below. At mid-ocean ridges, plates move apart and new oceanic crust forms as molten rock rises and cools. These ridges are long mountain chains beneath the sea. They mark places where Earth's surface is being renewed. The new crust spreads outward from the ridge, carrying the seafloor away on both sides. Magnetic minerals in the cooling rock preserve records of past changes in Earth's magnetic field, creating striped patterns on the seafloor. These patterns helped confirm seafloor spreading and plate tectonics. At subduction zones, one plate sinks beneath another into the mantle. Subduction means downward movement of a plate into Earth's interior. These zones create deep ocean trenches, volcanic arcs, and powerful earthquakes. As the sinking plate descends, it carries water and minerals downward. This can help generate magma above the slab, feeding volcanoes. The motion is slow, but stress can build along locked faults for centuries before being released suddenly as an earthquake. The ground then moves in seconds, revealing the stored motion of plates. Continents move with the plates. They do not drift freely across the ocean floor. They are embedded in thicker, lighter parts of the plates. Over geological time, continents collide, split, rotate, and gather into supercontinents before separating again. Mountain ranges rise when plates converge. Rift valleys form when plates pull apart. The present map of the world is a temporary arrangement in a much longer tectonic history. The surface seems stable during a human life, but the crust is always part of a slow planetary circulation. Earthquakes show that the crust contains motion even where land appears still. Along faults, blocks of rock are pressed, pulled, or sheared by plate forces. A fault is a fracture where rocks move past one another. Most of the time, friction holds the rocks in place while stress increases. When the stress exceeds the strength of the locked area, the rocks slip. Seismic waves then travel through Earth, carrying energy from the sudden movement. These waves reveal both the earthquake and the structure of Earth's interior. Volcanoes also express deep motion. Magma rises where rock melts in the mantle or crust. Some volcanoes form above subduction zones, others at rifts, and others above hotspots where warm material rises from deeper mantle regions. A hotspot is a long-lived area of volcanic activity not always located at a plate boundary. As a plate moves over a hotspot, a chain of volcanoes can form, with older volcanoes carried away and new ones forming above the source. This creates a record of plate motion written in rock. At the boundary between ocean and crust, Waves, currents, tides, and uplift reshape coastlines. Land may rise after ice sheets melt, because the crust rebounds when weight is removed. Other coastlines sink as sediment compacts or plates bend. Sea level also changes as ocean water warms, ice melts, and ocean basins shift. The edge of land and sea is therefore a meeting place of many motions, some daily, some seasonal, some geological. At this inner planetary scale, Earth's movement is no longer only a path through space. It is also the circulation of water and stone. Oceans carry heat and salt through basins. Tides lift and lower seas and ground. Plates slide, sink, spread, and collide. Mountains rise slowly while seafloors open in darkness. The solid surface and the deep oceans share all the larger speeds of Earth. Yet within that shared journey, they create their own patient movements, shaping the planet from the outside inward with water, rock, gravity, and time. Inside the moving oceans and crust, the human body occupies the smallest region of this layered motion. It stands, rests, walks, breathes, and sleeps on a surface that seems still because nearly everything nearby shares the same movement. The ground, air, water, buildings, trees, and bodies are carried together by Earth's rotation, Earth's orbit, the Sun's galactic path, the Milky Way's local motion, and the expansion of the distant universe beyond bound systems. At human scale, speed is mostly hidden by shared motion. A person at rest on the ground is not motionless in a physical sense. The body turns with Earth once each day. It follows Earth around the Sun once each year. It follows the Sun around the center of the Milky Way over hundreds of millions of years. It also shares the wider motions of the galaxy among neighboring galaxies and through large-scale cosmic flows. These motions do not need to be felt to be real. They are measured through astronomy, geodesy, spacecraft tracking, and the physics of light and gravity. The body does not sense constant speed directly. It senses acceleration, pressure, vibration, balance, and changes in motion relative to nearby surroundings. In a smoothly moving train, a seated passenger may feel still if the train does not speed up, slow down, or turn sharply. On Earth, the same principle applies more deeply. The planet moves smoothly enough, and all nearby objects share its motion closely enough, that the body does not register the enormous speeds involved. The inner ear responds to changes in motion, not to steady travel through space. Gravity gives the body its strongest daily sense of direction. It pulls matter toward Earth's center, pressing feet against the ground and giving weight to muscles, bones, blood, and organs. Weight is not a measure of cosmic stillness. It is the local force of Earth's gravity on mass. While the planet moves through space, gravity holds the body to the surface and keeps the atmosphere nearby. This local pull defines up and down far more strongly than any awareness of orbital or galactic motion. Earth's rotation slightly reduces apparent weight near the equator because the surface moves in a wide circle. The effect is small. Gravity remains much stronger than the outward effect of rotation. The body remains firmly bound to Earth. The difference in apparent weight between equator and pole is measurable, but it is not dramatic in daily life. It shows that even the quiet act of standing involves a balance of gravity, rotation, and the shape of the planet. The body also moves with the air. Near the surface, the atmosphere usually shares the rotation of Earth, though winds create local differences. A calm room is not sealed away from motion. The air inside it turns with the planet and follows Earth around the Sun. Breathing draws this moving air into the lungs, where oxygen passes into blood and carbon dioxide leaves it. The exchange is intimate and small, yet the air itself belongs to the same moving atmosphere described by weather, circulation, and planetary rotation. Blood moves inside the body through vessels driven by the heart. This circulation is tiny compared with cosmic scales, yet it is another form of motion nested within larger motion. The heart pumps, the lungs expand, cells exchange molecules, and nerves send signals. Atoms within tissues vibrate because of temperature. Molecules diffuse through fluids. None of these inner motions contradict the larger motion of Earth. They occur inside it, carried along with it, like small ripples inside a vessel moving smoothly across a broad sea. At the scale of atoms, matter is never still. Electrons occupy quantum states rather than tiny classical paths like planets. But atoms and molecules in warm matter move, rotate, and vibrate. Temperature is linked to this microscopic motion. A sleeping body, a stone floor, a wooden wall, and a quiet glass of water all contain restless molecular activity. Stillness at human scale is therefore an experience, not an absolute condition. It means balance, shared motion, and no strong disturbance. The senses are tuned to local survival, not to the full motion of the universe. Eyes detect light, shapes, and movement across the visual field. Ears detect pressure waves in air. Skin detects touch, heat, cold, and pressure. The vestibular system in the inner ear helps maintain balance by sensing acceleration and orientation in gravity. These senses evolved for walking, reaching, listening, and remaining upright on Earth. They do not directly reveal the planet's orbital speed or the Sun's galactic path, because those motions are shared and steady. Scientific instruments extend perception. Telescopes measure the redshift of galaxies. Spacecraft measure the solar wind. Satellites track Earth's rotation, gravity, and shape. Atomic clocks reveal tiny changes in timekeeping caused by motion and gravity. Seismometers record the motion of the crust. Buoys and satellites measure ocean currents. Weather instruments follow moving air. Through instruments, the quiet ground becomes part of a vast moving system, and the body's stillness becomes a local condition inside many measured speeds. The human scale also shows why no single speed describes reality completely. Speed must be measured relative to something. Relative to a chair, a resting body may have no motion. Relative to Earth's axis, it moves in a daily circle. Relative to the Sun, it follows Earth's orbit. Relative to the galactic center, it travels with the Sun through the Milky Way. Relative to the cosmic microwave background, it shares a still larger drift. Each statement is correct within its frame. Motion is not erased by choosing a smaller frame, and stillness is not false when defined locally. This layered truth is calm rather than disruptive. Nothing in ordinary rest requires the body to resist the full speed of the planet through space. Shared motion removes the feeling of rush. Gravity supplies steadiness. The ground supports weight. The air moves with the surface. The senses settle into local balance. Meanwhile, Earth turns, orbits, and travels with the Sun, and the Sun moves through the galaxy, and the galaxy moves among larger structures. At the innermost region of this path, the human body is a small moving system within a larger moving world. Its bones hold shape, its blood circulates, its lungs exchange air, and its cells maintain life while all of it is carried through space. The reality of speed is not only distance crossed quickly, it is belonging to nested motions, each one real at its own scale. A quiet body on quiet ground is still in one frame and swift in another. Both are true. The universe allows this layered stillness, where immense motion can pass unnoticed because everything close moves together. The motion settles into a quieter understanding. Across the widest distances, space expands. Within the cosmic web, galaxies drift under gravity. Inside the local group, the Milky Way moves with its neighbouring galaxies. Within the galaxy, the Sun circles through the disk. Around the Sun, Earth follows its yearly curve. On Earth, the surface turns, the air flows, the oceans move, and the crust shifts slowly beneath all familiar places. At the human scale, these motions do not arrive as noise or force. They are shared by the ground, the walls, the air, and the body. Stillness remains real in the local frame. A resting hand is still beside a resting table. A sleeping body is still within a quiet room. The larger speeds continue without needing to be felt. Gravity holds the body gently to Earth. The atmosphere moves with the surface. The planet carries its oceans and mountains through space without tearing them away. The universe does not require a single meaning of rest. Rest depends on the frame being used. Motion depends on what it is measured against. A body can be calm on Earth and also part of a planet moving around the Sun. Earth can be steady in its orbit and also part of a solar system moving through the Milky Way. The Milky Way can hold its stars and still drift among galaxies. The final picture is simple and layered. Nothing nearby needs to rush past for the great speeds to be true. The body remains held in a small region of balance, while larger motions unfold beyond direct sense. The ground supports, the air surrounds, the planet turns, and the night carries distant light from moving worlds. In that shared motion, stillness becomes a local piece within a universe that is always moving.